All right. Yeah, so I'm going to be talking about how you can use knowledge graphs to help improve your observability. But before I do that, let me just quickly introduce myself. My name is Homin Lee. I'm a data scientist at Datadog, which is a monitoring company. My team and I focus on creating features that automate anything that you might use our service to do, you might do manually using our service. So we like to help reduce your toil. Before Datadog, I was a data scientist at various other companies, small startups usually, building large-scale machine learning systems. And before that, I spent way too much time in academia. I got a PhD in a field called computational learning theory, very tiny field. And what we do is we prove theorems about what's possible or not for computers to learn. All right, on to the talk. We're here at Monitorama, so presumably most of you work for an organization that cares about observability. And what are you observing? Well, maybe your hosts, your containers, what are they up to? If they're having issues, are they like service-wide, or maybe it's at the level of a cluster or a region? And speaking of services, how are yours organized? Maybe you have a ton of microservices, or maybe you have a giant partition monolith. Or maybe you have that monolith and now you're transitioning to microservices. So those microservices are doing some things, and your venerable monolith is still doing a good amount of traffic. And these services are running on those hosts and containers from before. And maybe you have some teams that are like, servers, we don't need your servers, we're serverless. All right, so to properly observe what's going on, you collect metrics whose cardinality reflect not only the size of your infrastructure, but the cardinality of the types of requests and data that are being processed. And maybe you have some distributed tracing going on. So you have these spans coming from all your microservices and that handle your requests. And so you're getting much finer grained detail. And these are great. They're a little harder to roll up, but much more detail. Then you probably also have event data, also lots of detail, lots of fields that can track everything from deployments to individual user interactions. And of course you have logs where developers have kindly told you what's going on in excruciating detail. And some of it's useful, and there's a lot of it for you to collect and store and process. And so now that you have your metrics, trace, events, and logs, what do you have? Total information awareness, which is like a wonderful state to be in, because what could you possibly do with that? Maybe you could try to do some root cause analysis. So ideally, like what happens? You get woken up at 3 in the morning by some anomaly detection alert, and it's a good algorithm. It's not warning you about some one-off spike that you don't care about. It's like a real increase in error. It's about some service that has like an actual amount of traffic. And you're like, okay, great, I got woken up, what do I do? And it shows you like a handy dandy like stack trace, and now you see that those errors are like timeout errors. So you go to your handy dandy service map, and you see, okay, this service that I got woken up about, it handles these customer requests. It itself makes requests to some service B, which makes requests to some database. Oh, and hey, look, like our monitoring system automatically detected that B is lagging. So B is lagging, makes sense that A is timing out. And then it turns out that some host on the database is running out of memory. And then now you have like a kind of like good idea where to look, and maybe it turns out some customer is sending you giant JSON blobs in some text field, and the database is choking on indexing it or something. So you had this amazing observability. You're in this like beautiful, ideal environment. That root cause analysis was pretty easy. And you might wonder like, hey, like that was so easy. Like maybe you can just automatically surface all the contributing factors, right? How great would it be if you get woken up at 3 in the morning because something's going wrong, and the alert not just tells you like, hey, this is what's going wrong, but these are the possible causes. And then, yay, like life would be all double rainbows. You probably see where this is going. So like, let's say you get woken up at 3 in the morning, your anomaly detection algorithm is still doing its job, But this service is like an intern project. Why it's up on prod, I have no idea. And yes, it's serving like, a fair amount of traffic, but it's not real traffic, it's all simulated. Or like maybe, service A is a real service and you go to your service map and you see that and you're like, oh gosh. And maybe the situation is the same as before. A talks to B, talks to this database, but B is nowhere to be found on the service map. And maybe this is because you create the service map because you tag things like with service colon A, service colon X, service colon Y, except for the team that's in charge of B decided to call it LSV systype B. I have no idea why. It probably means something to them, but it means nothing to me. And then, we detected that it was lagging, but since it's disconnected to everything else on that map, didn't see it. Or maybe you're creating this map using tracing, but for some reason that team decided not to instrument their service. Or maybe, like everything's the same as before, like A, B database, you have the nice map, but your database hosts are behind a proxy, so you have like no idea what's going on under there, and you can't connect the two things. So often, your observability data kind of looks like this. And so on that depressing note, let's make a quick aside. Remember when I said that I had a PhD certifying that I was an expert in this tiny, tiny field? Well, that clearly gives me the expertise to make pronouncements about completely unrelated fields. So the field that I like to, I haven't actually studied, but I like to make pronouncements about is organizational theory. So organizational theory studies like social units of people, how they're structured and managed. It's a field that's kind of driven by anecdote and analogy, and since I have anecdotes, All right, so there's this thing called the mirroring hypothesis, also known as Conway's law, and you might have heard the phrase, you ship your org chart. And so basically the idea is like, if you're using a product and you're doing something in one part of the product, and then you go to some other part of the product and you're doing exactly the same thing, but it has a completely different feel to it, that's probably because two teams very far apart from each other in the org chart implemented the same thing, and they had no idea that the other person was doing that either. The same thing, and that's what happened. There's studies on this where people will look at org charts, they'll look at their products and be like, oh, these kinds of match up. And then they'll be like, oh, there are exceptions, like these don't match up, but whatever. So my well-informed corollary to this is that observability follows your org chart. And so what do I mean by this? So let's say you're on some app team and you're instrumenting your code and you're sitting next to someone else on your team who's implementing their things that they're implementing their own things, but they probably instrument things in a very similar way. Their keywords, their tags, they make sense to you. And then maybe you're sitting next to a storage team, and because your APIs ultimately get their data from their databases, and so they care about databases, database things. They instrument things in a different way. They care about different things, but because you guys sit next to each other and you talk to each other, you probably understand all of their metrics also. But there's like another app and storage team completely far away in the org chart, and chances are you actually have no idea what those things do, and they're probably completely obscure to you. Another example of how things can happen is let's say you have this old legacy system that has old legacy instrumentation, and now you're in the process of migrating to fancy new microservices with the latest and greatest in observability practices, JSON logs. And you're doing all that, but for a long time, you're going to have the legacy instrumentation and the newfangled instrumentation going at exactly the same time. And then just my final example is, let's say you acquire a new company, or you want to start a new product and you spin off a team, and maybe they have completely different tools than the rest of the company, maybe a completely different language about how they talk about things. And so, yeah, that's another example of how observability can follow your org chart. All right, second anecdote is something called Gore's hypothesis. So Mr. Gore, this is of Gore-Tex, the fabric fame. Apparently the story goes that he's making Gore-Tex, his company's getting successful, and he has more and more employees, and I guess they're building could only fit 150 or something. And now there's more employees, and so instead of moving to a bigger office, he just created another office building of a similar size, because his theory is that if you don't know the people you're working with, you'll be much more inefficient. So like, if you don't know people's names, or you don't even recognize their face when you pass them in the lobby and have like a vague idea of where they work, then he thinks that things will be much more inefficient. A little after that, this primatologist named Dunbar, I guess, was studying the social structure of primates. And so he made some field observations of primates and their social structures. And I guess they topped out at 150 also. And going from that anecdote to analogy, he said that probably for humans also, you can't really know more than 150 people. And then going from analogy to conjecture, some people say that after 150 people, things devolve into anarchy and chaos if there is not rules or regulations or a police force. All right. So my corollary to that is that if you have more than 150 employees, your observability standards have completely fallen apart. And then, like any great, you have like two great theories. What do? You make a synthesis. And so without enforcement, your observability standards are going to completely fall apart after 150 employees. But I'd say all's not lost. Like, you still can kind of follow things through the org chart. And that first clause, I think, is important, like without enforcement. So like, if you happen to work for an organization that has an observability team that is actually maintaining standards, then like, you're in the Holy Land. This is great. And really, like, I think like all the talks before this one, like basically like listen to everything they say, do those like great standards, and standardize your instrumentation. But maybe this is actually your real actual current situation. You want rainbows. Let's see if we can piece together rainbows from what we have. So how could you do root cause analysis with this data? So just to recap, the situation we're in is that we have this like large-scale, messy, inconsistent observability data. And labels are pretty hard to come by. And by labels, I mean like me going to the team that's in charge of that thing B, and me asking them, hey, is LSV systype what you mean by a service? And then they'll write back, what do you mean by a service? And then I'm like, all right, let's like set up a meeting. We set up a meeting, I do an interview, and then they're like, I ask this question again, and they're like, what exactly is a service? And then we have a very long, fruitful discussion, or at the end, like, I actually have no idea if LSV systype is a service or not. Or like, a lot of times if you want to do for root cause analysis, it's great if you have these like detailed postmortems that tell you exactly like, what, this is like that data that we have, this is what we've observed, and like bam, 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 like this is how we can see like what the cause was. But of course, like, you don't always have these beautiful postmortems. Ops people are busy, like the thing on the top of the stack is what they care about the most, and they're off to fight another fire. These like postmortems can like fall by the wayside. Let's say like you can get these labels, but they're few and far between. But on the positive side, I think like we have a lot of domain knowledge, right? So like system metrics, there's a lot of tried and true wisdom about them. Like databases act in a certain way that we know. And then we also have a lot of user interaction data. So I think this is important that you know which metrics that your colleagues care about. Like, I don't know what LSV systype is, but man, does that team care about that tag, and that like, and they like refer to everything by that. And so as a data scientist, when I see these four things, I think large scale messy data is machine learning. It's gonna have to be unsupervised or semi-supervised at best because you don't have that many labels. We have these known entities, and then we have relations between them. And then putting those four things together, I think of knowledge graphs. So a graph is just nodes and edges between nodes. And what makes a graph a knowledge graph is that they have a thing called an ontology, which is just a fancy way of saying that these nodes are like specific things. So in our case, these nodes are things like metrics, dashboards, users, teams, services, or it might be like log patterns or specific types of spans. So let me just give you an example. So let's say you're getting woken up at 3 a.m. by this alert. That's a node in the graph. And it's immediately attached in the graph to 3 other things. So this alert is on some metric, right? So it's attached to that. This alert alerts some particular team that you're on call for. And then somebody has helpfully annotated this alert with service S, saying that this is an alert about this service S. And so now you know something wrong with this service. And then let's say you get paged by another alert on a different metric. Unfortunately, whoever created this alert has not helpfully annotated it with what service is about. But maybe in the graph, there's this edge between those two metrics saying that when metric M goes up, it's a leading indicator for metric N going down, and this always happens historically. So now you'll get a pretty good sense that all right, not sure what this second alert is about exactly, but it's probably very related to the first one. Right, now, so let's say the original metric is on some dashboard. So I think dashboards have gotten a bad rap recently, but I think they're actually probably one of the most useful pieces of monitoring tools out there. Dashboards that are well constructed, and once again, they should listen to Corey's advice from yesterday. They have metrics that are chosen with care and that are related to one another on there. And so just by looking at the most popular dashboards that people look at, you can probably actually recreate a service map because they're going to include the service that the dashboard is about, but also related services, things like that. So anyways, let's say this particular metric is on some very important dashboard that lots of people look at. And then let's say there's another metric also on that dashboard that has an alert going off. It's not paging you. And also, once again, whoever set up this alert was lazy and didn't include any nice tags saying that it's about a particular service. But you have these tentative edges going from that alert to this another service R. And why do these edges exist? Well, the system noticed that the message on that alert might not have had an explicit tag service R, but somebody wrote R, the CPU is high in R, and then the handy text matching can be all right, this is probably about service R. And then not only is that, the metric itself is tagged with something like role R, and it knows that this particular tag key is something that's often used to refer to services along throughout the organization. And then on top of that, maybe on the service map, you can see that S calls R. So this is great, right? Been woken up by this alert. This other alert's going off on an unrelated service that's not part of your team, but it's a dependency of your service. And so then maybe that's why that alert is going off. On a slight side note, let's say the original metric is also in some dashboard that was nobody looks at, right? Maybe say the last time it was viewed was months ago, and maybe that has a metric on it with some alert, but there's no other information connecting that metric or that alert to the rest of what else is going on. Then we might think all right, absent any other information was probably not related to what's going on. Maybe it is, maybe it's not. And even more importantly, right, you're working at an organization with more than 150 employees. There's probably a lot of services. So these other alerts X, Y, and Z that are not connected at all to this, you can just completely ignore. They're just, you're almost entirely certain that they're not related. Okay, so let's say this is the picture that goes on in a service map. R calls another service V and two databases, and then you can just automatically scan all their read and use metrics, say, and then it pops out that some particular metric from some database is looking bad. And so this is how you can use something like an observability graph to get to the bottom of what's going on. And of course, as a user, you don't want to see this. But this can be like what goes on in the background for just that, right? This is kind of what we saw. So to conclude, say that machine learning and knowledge graphs save the day, but that's not the actual conclusion. The actual conclusion is that all of the observability data that you collect was created by people, very well-intentioned people, who put it there to be useful. And because coordinating people is hard, a lot of that data might be unintelligible to you, like at face value. But if you look at how people are interacting with this data and using this data, it's not that hard to actually recover what's important, what's not, and how they're related to one another. And so that's it. Thank you.
Any questions? Anybody? Awesome. Oh, wait. Oh, sorry. Up there.
The question is how users use this graph at Datadog. Also, if there's a UI and, yeah. So basically, the knowledge graph is used to power various features that we're developing to do this, like automatically surfacing contributing factors to any alert that goes off. We don't expose a UI per se for now, mostly because, as you saw before, the thing that you can get back is a tangled mess, and like it takes some, I would say, knowledge in how those models work and how to interpret them to know like when those edges are something that you can trust or not, and when there's enough evidence for like that example before, where like being able to know that alerts C and Metrico are actually related to service R, it's like kind of it's all built into the back end, and so yeah. So I would just say like this is what's going to power a lot of our machine learning features that are going to have their own front end in a different way. Yeah. Yes?
So when you're talking about building out this graph, you're talking about people forgetting to add a relationship or add an attribute. I'm curious what the percentage of building this knowledge graph is manual for user entry and anything that you potentially automated.
The question is whether these graphs are built manually or automatically, and they're all automatic. So, like, and before the question was like whether or not, because people don't, or sorry, the audience member asked, I said that a lot of this stuff had to be done because people weren't filling out useful metadata alerts and stuff. And so yeah, like exactly, like if everybody filled out everything consistently across the organization, you wouldn't need this. Like, I think you'd be in that ideal scenario from like the beginning where you can just kind of like turn the crank and like it'd be much easier to figure out how everything was related to one another. But this is like an automatic graph creation that happens just because we need this, because things aren't consistent. Not everybody's filling everything out, and so we're trying to infer as much as we can from the available data that we have. I mean, that'd be great, but if they're going to do that, they should just label everything consistently. and like, you know, like there was another talk, I think yesterday, about like how to like make useful messages on your monitors, and like really please do all that. That would be so much better. Yep. It's hard. I mean, like all unsupervised learning things, right? It's like, it's hard. And like a lot of interviews. Well, thank you.